used for material shear. Which is also the case with the weak rocks under low confinement. For given cases, the strength of rock mass is characterized by cohesion, friction angle, using major and minor compressive stresses. The Moore Coulomb-Fedier criteria is also considered to be reasonable approximation for discontinuity, typically using cohesion as a 0, whereas friction angle controls the strength envelope. To assess the failure along the discontinuity, joint failure criterion is used with substitution of stress components that is normal and shear along and near the discontinuity. So this study is a quantitative analysis carried out for the factor of safety, percentage of model cases with slippage along the faults, displacement around the tunnel boundaries. Factor of safety and displacement around the tunnel boundaries are intrinsic outputs of FLAG 2D, whereas for the percent of model cases with slippage have been done by adding Python code to use Monte Carlo simulation. Evaluation of fault is done with a Moore Coulomb failure criteria, as I mentioned earlier. The figure shows here the strength, shear strength of the discontinuity if equal or less than shear stress in the region. That area or that region will be the span of fault slip. This is the case for 61 meters depth as shown here in the figure. The slip span is 7.5 meters. A fault slip is not significantly sensitive to a single input parameter. Rather, it shows higher susceptibility in combination of input parameters, which led to include Monte Carlo simulation to evaluate percentage of model cases with fault slip. The Python code is used to simulate 1,000 iterations with a truncated values of normally distributed for given parameters between -2 standard deviation to 2 standard deviation. Whereas uniform distribution of K ratio was used considering 0.4, 0.5, and 0.6. The figure shows here distribution of randomly generated cohesion values used for Monte Carlo simulation.
Thanks, Mohammed. So just to quickly remind everyone of the steps that we took to quantify the model, which Mohammed just went over, we performed sensitivity analyses on both the rock mass and the fault strength input parameters and how these input parameters affected the model's factor of safety and whether or not the fault or faults slipped. We then performed a Monte Carlo analysis to determine the percentage of slippage along the fault or faults. We performed a factor of safety calculation for the entire model using a shear strength reduction method, which is intrinsic to FLAC. And then we also looked at deformations in the model. So getting into the results now, we performed the sensitivity analyses, as I mentioned, for the fault and the material strength input parameters. And we did this for a model scenario with a tunnel depth of 61 meters, which is the minimum allowed per the design criteria. And we found that the factor of safety plotted on the x-axis here was affected by the strength of all input parameters listed here, where an increase in the parameter's value led to an increase in the factor of safety. However, the amount that the factor of safety was affected was relatively small, with the exception for the material's cohesion, which had a especially large influence on the model's factor of safety. So based on these sensitivity analysis results, we decided to play it safe and perform the factor of safety model analysis using a worst case scenario, where all of these strength input parameters for both the material and the fault, all of their values are assumed to be 2 standard deviations minus their mean parameter value as provided in the prompt. And Mohammed touched on this a little bit earlier. And we did a similar sensitivity analysis for fault slippage. We wanted to understand how these model inputs, both the material and the fault strength properties, affected slip along the faults. So this analysis was done for the single fault case with a tunnel depth, again, at its minimum position of 61 meters. And you can see from the results of these 4 figures that varying any one single input parameter didn't produce a trend regarding if the fault slipped or did not slip. And this was true for the material's cohesion, tensile strength, friction angle, and also the friction angle of the fault. So this means that fault slip is actually triggered by a combination of all of these strength input parameters. And this validates our usage of the Monte Carlo statistical analysis for evaluating percentage of slip, where multiple combinations of all of these strength input parameters must be tested for a comprehensive slip analysis. So our team calculated both the factor of safety and the percentage of slippage for the single fault case scenario, which is plotted here on the left. So you can see from this blue line that as the depth of the tunnel increases, which is plotted on the x-axis, the model's factor of safety, plotted on the y here, it also increases. And if you look at the orange line, you can see the reverse trend where increasing the tunnel depth decreases the percentage of slippage along the fault. So again, our goal is to achieve the design criteria of a minimum factor of safety of 1.5 and a maximum percentage of slippage of 5%, but while also minimizing the tunnel depth. So the design criteria are both met at a minimum tunnel depth of 63 meters, which we've indicated with this black dashed line right here. At this tunnel depth, the factor of safety of the model is 1.53, which is above the design criteria of 1.5, and the percentage of slippage is 3.3%, which is less than 5. Therefore, our final design for the single fault scenario is shown here on the right, where the tunnel depth is placed at 63 meters below the surface. And we also looked at deformation in the model at 3 different locations: at the surface of the model, plotted in purple, at the crown of the tunnel cross-section, plotted in green, and at the floor or the invert of the tunnel cross-section, plotted in red. So you can see that the model deforms more and more as the time steps are marched, which are plotted on the x-axis here. Eventually, the deformations all reach this relative plateau, which is when the model reaches equilibrium. And the maximum deformation in the final time steps at these 3 locations is at most just below 3 centimeters, which is a negligible amount of deformation that can be easily mitigated with ground support. So this means that our final design can be reasonably constructed. And these same analyses were also performed for the double fault scenario. But for this case, we had to analyze percentage of slippage along both the upper and the lower faults. So again, if you look at this blue line on the figure on the left, you can see a similar trend to that of the single fault scenario, where increasing the tunnel depth increases the factor of safety. Increasing the tunnel depth also decreased the percentage of slippage on both faults. So actually, the percentage of slippage of the top fault is always below 5%, no matter the tunnel depth that we tested. But the real challenge with this subsurface scenario is actually with the bottom fault, which has nearly 100% percentage of slippage for all tunnel depths modeled up until a tunnel depth of 72 meters, which is indicated by this black dashed line. At this tunnel depth, the factor of safety of the model is more than 1.6, and both of the percentages of slippages for the top and the bottom faults are less than 5%. So this is now an acceptable design that meets all of the design criteria. Therefore, for our final design, for the double fault scenario, we place the tunnel at 72 meters depth, which places it below both the top and the bottom faults. And again, we looked at deformation at those 3 locations in the final model to ensure that they were sufficiently small. The largest displacement is a little less than 4 centimeters for the double fault case, which is negligible and can be easily mitigated.
Hey, thank you very much. Here we come with the risk and mitigation strategies. Regardless of the construction method, risk and mitigations are assessed after choosing the tunnel depths for 2 scenarios. Keeping in view both scenarios, TBM tunneling will mitigate most of the risks, but in case of NATM or SEM tunneling, the critical sections may have a discrete block fallout, which can be mitigated by providing systematic rock support. Another scenario is tunnel convergence that may be symmetrical or asymmetrical, that requires continuous monitoring to analyze against critical values, and then a support system can be decided accordingly. Water ingress can be disastrous because, as we mentioned about the top fault, so it requires systematic grout campaign irrespective of construction system. Fault slip, definitely it will lead to associated risks, as fault slip requires continuous monitoring to decide the appropriate support system for that. Tensile stresses at the discontinuity will lead to thickening of the fault, which will also cause slippage. Monitoring will indicate the requirement of appropriate support system here. So we are concluding our design with a single fault and double fault scenarios, placing the tunnel at 63 meters and 72 meters respectively. And you can see the criteria have been met, factor of safety greater than 1.5, and percentage of slip is less than 5%. I appreciate your patience, and here we are open for question answer.
Thank you so much, Team Rockbusters. Judges, the floor is all yours.
Hi, this is Lauren. Nice presentation, guys. I'm a little bit unclear about the initial stress assumption. Could you say a few words about that and how you feel about that?
So you mean like stress initialization in the model?
Yes.
Yeah, we actually have a figure for that. Here we go. So yeah, so we made sure that our stresses were initialized correctly. So this is the plot from our model, and this is at the minimum 61 meter tunnel depth. And we compared the depths, the stresses at various depths, and we did a computation given the density of the material. We made sure that that number that we computed by hand was equal to that of the model to ensure that everything was correct.
So that's the vertical stress. What about the horizontal stress?
For the horizontal stress, for the horizontal stress is we already mentioned regarding the K values. We try to calculate the same K values for the modeling in that sense, but we haven't got a calculation of the horizontal stresses in that sense, what we did for the vertical stress. Based on the vertical stress, we finalized our model and we started, further calculation based on the numerical analysis, which we done already shown.
So if I understand you, I think you mentioned 0.4, 0.5, and 0.6. Is that right?
Yeah.
Those were the cases that you looked at?
Yeah.
Okay, thank you.
I'm wondering
Questions?
why that small a depth difference makes that much of a difference with regard to slippage and safety factor.
For the single fault scenario or the double fault?
Well, particularly for the single fault, but
so you're asking like why a small change?
you talk about 1 meter difference and the major difference in both factors. Why?
Okay, so your question is like, why does a small change in the tunnel depth increase the model by such a large amount?
Yeah, and this the other way around also for the slippage.
Yeah, for sure. So in regards to the displacement, the slippage on the fault, I think like there's this zone of influence around the fault, and when the tunnel is within the zone of influence or very like close to the zone of influence, it's going to the rearrangement of stress concentrations around the tunnel cross section is going to affect the fault a lot more and trigger slip. But then once you get away from the zone of influence and put the tunnel deeper and deeper, then it starts to level out and have a significantly smaller percentage of slippage. And then for factor of safety, I mean, I think it's fairly consistently increasing here. So this is, in my opinion, due to increased stress from like overburden and increased confinement on the tunnel. Do you have anything to add, Mohammed?
Yeah, obviously that is actually based on the influence zone. The tunnel closer to the fault one, which is also, we mentioned about the water barrier. So after that, if you are out of that influence zone within that location under that fault, we saw a reasonable, like a significant change in the fault slippage change. You can see like even in 63 meters, we went below the critical, criteria, which was mentioned in the problem statement.
Thank you.
2 quick questions. This is John Dudley. Statement did not specify Young's modulus and Poisson's ratio. What did you use? What criteria did you use to specify those? That's my first question.
In the model, which was initialized by Itasca, there were some properties which were not mentioned in the prompt, but those were mentioned there in the initial model. So most of the properties which were given, only dilation angle was considered as 0 in this case. Other than that, that was given by the model which was provided with the problem statement.
So you simply used what Itasca had in their template.
Absolutely.
Okay. Second question. You did Monte Carlo simulation. Did you include the Young's modulus and Poisson's ratio in that? And if so, did you? No, you didn't include
No, we
that.
didn't.
No,
Only
no.
the strength parameters.
Only the given parameters were used for simulation with the Monte Carlo. Other than that, whatever particularly assumed is the dilation angle and the Poisson's ratio, which I mentioned that with the initial code, which was not used as a parameter for Monte Carlo simulation.
Yeah, we didn't have like the standard distribution, standard deviations information for that either. So that's why we just stuck with one value.
Okay.
Okay, thank you, judges. Thank you, Team Rock Blasters.